Right, so in this case, did we need to simplify root 3? No, there's no way to simplify it. You just leave it as it is, and you move on to the next step. The second step in rationalizing the denominator of these single term denominators is the wording that I would use a little bit different so it applies to everything. And the way that I describe this is I'll ask you to build your radical up to higher terms. In order for it to be a perfect power equal to the index. Okay, what that means is you're building up your radical so that it fits this form. Whatever your index is, it's the nth root of some base to the nth power. And the whole reason for that is if you have the nth root of a to the n, that index of n and that power of n cancel out completely, leaving just your base a. And so that's going to get rid of the radical from your denominator. Okay, and so that's the step that we did right here. We took our same index as we build this radical up to higher terms. We're going to take our same index, the square root, the same base 3, and we're going to build it up so that it eventually becomes this form, the nth root of 3 to the nth power. Well, our index is a 2. So if you think about, you need to build the 3's up so that there's 2 of them, a total of whatever number the index is. So how many 3's did we have in our original expression? Just 1. So how many more do we need when we rationalize it? To get to the number 2, we need 1 more. So it's that number over itself. Again, this is the identity property multiplication. Okay? Multiplying by a value of 1 does not change the identity of an expression. And so that gives us this form. And so now when we perform this last step, which is just to simplify completely, okay, we just multiply across the top. 4 times root 3 is 4 root 3. Multiply across the bottom. Root 3 times root 3, we built it into this form, so all we're going to be left with is the base 3. Okay. All right, I want you to see if you can rationalize this expression on your own here really quickly. Okay, 1 over root 20. Okay, see if you can go through the steps to rationalize following these 3 steps. Okay, step 1, simplify your radical. Are there any perfect square factors we can remove from 20? This is 4 times 5. The square root of 4 comes out as a 2. The factor of 5 stays inside our radical. Okay, so there's our first step. Second step, we're going to build up when we rationalize this denominator, we're going to build up our radical. So we're going to use the same index, so square root, the same base. The lowest base we can possibly express here is 5. And when we build this up, we need a total number of 5's to equal the index of 2, square root. So we had 1 to start with, so how many more do we need? Just 1 more to reach 2. And so as we multiply across the top, we get root 5. Across the bottom, we have our multiplier of 2. Root 5 times root 5, again, it fits this pattern. The nth root and the power are exactly the same. They're both 2's, so we're left with just that base of 5. And so when we simplify it completely, we wind up with root 5 over 10. Okay. All right, I want you to try one more example of this, and then we'll move on to a little more challenging ones. Okay, so see if you can rationalize 4 over root 10. Hi, step 1, can we simplify this radical? No perfect square factors that you can remove from root 10, so let's go ahead and build up, rationalize our denominator. We'll build up our radical, same index, same base. We need the total power of 10 to be equal to the index, which is 2 for square root. We had 1 10 to begin with, so how many more 10's do we need? Just the 1. So when we multiply across the top, 4 root 10, across the bottom, root 10 times root 10, again it fits this pattern. Index and power cancel, leaving just the base of 10. And then simplify. 4 and 10 have a common factor of 2. 2 goes into 4 twice. 2 goes into 10 5 times. And so you wind up with your answer, 2 root 10 over 5 as your final answer. So questions on that. So this is as far as you guys went in algebra. You probably only rationalized denominators that were square roots. Okay, but what's going to happen if you get something that is something other than a square root? Okay, so let's take, for example, a cube root. And so if you had to rationalize the expression 2 divided by the cube root of 6, you can still follow all these same steps. Simplify your radical first. Now, part of simplifying the radical would be to remove any perfect cube factors from this, but also a part of this simplifying is look to express your base in the smallest exponential form as possible. So, can you express 6? Is 6 a perfect power? No. So you leave it as it is, and we're going to follow step 2. We're going to build up our radical using the same index. So in this case now it's a cube root. Using the same base, we found that our base was the given base 6. And now when you build this up, you need the total power for the 6's to be equal to the index. So the index was 3 to start with. Okay, how many powers of 6 did you begin with? 1. So how many more do you need in order to get a total equal to our index? You need 2 more. So when you rationalize, that determines how you rationalize this. So now multiplying across the top, we get 2 times the cube root of 6 squared, and you can actually just expand that out. So 36. And that's all over. Again, it fits this pattern. The index and the power are both going to be 3. So you're just going to be left with your base 6. Now you can simplify this fraction further. 2 goes into 6 3 times. And so you get your overall answer of cube root of 36 all over 3. And did everybody see the process that I went through on that? Okay, I want you to try on your own. See if you can rationalize this radical, please. Okay, the cube root of 3/5. Right, the first step in this is, again, you can't have a fraction inside a radical. So what I'm going to do is I'm going to apply this radical to the numerator and denominator independently. And then I'm going to go ahead and start my steps. So can I simplify this radical in the denominator? There's no perfect cubes that are factors of 5, and 5 cannot be expressed as a perfect power in another exponential form. So we can go ahead and move on to the next step, which is to rationalize. When we rationalize, we're going to build those radicals up using the same index and the same base. Again, the base of our denominator was 5, so we're dealing with the cube roots and then a 5. And we need to build up this radical so that the powers of 5 are equal to the index. So the index is a 3 for the cube root. How many 5's did we start with? 1. So how many more 5's do we need when we rationalize? 2. That gives us a total of 3. So now as we multiply across the top, you get 3 times 5 squared under the same radical. Well, what is 5 squared? 25 times 3 is 75. And then across the bottom we're going to get cube root of 5 cubed. Again, it fits our pattern, nth root of 5 to the n. So we're just going to take out our base 5, and that would be our solution. Okay. All right, so let's go to what I would consider the most challenging type of questions that you are going to see in rationalizing single-term denominators, and that is something in the form like this. Okay, see if you can rationalize this denominator. Again, I'm going to give you just a short period of time to work on it, and then I'm going to talk through it. Now, if your first inclination is to multiply by the cube root of 36 squared over the cube root of 36 squared, that will eventually lead you to the right answer, but it winds up giving you numbers that are not easy to mentally calculate, right? Can anybody tell me 36 squared right off the top of their head? No, it's more work, right? But what do you notice about 36? It's a perfect square, right? You want to be able to recognize perfect powers, because if you recognize that this is a perfect power, this part of this first step here in simplifying the radical is identify those perfect powers. So instead of a 36, if we think of it as 6 squared, now we're working with a base of 6, not a base of 36. It's easier to manipulate. And so now when I work through my second step, which is to rationalize, build the radical to higher terms. I'm now going to use my cube root. My base is now a 6 instead of 36, so it's easier to manipulate. And when I count my powers of 6, they need to equal my index, which is 3. Now I started with how many 6s? 2. So how many more 6s do I need to rationalize with? Just 1. That gives me my total of 3. And so now when I multiply across the top, I get the cube root of 6. And the bottom, again, it fits this pattern. The cube root and the total powers of 6 of 3 cancel each other out, leaving just that base of 6. Now, if you had tried rationalizing with the cube root of 36 squared over the cube root of 36 squared, if you were able to simplify it, it would eventually simplify into this form. But again, it's much easier to reduce the base to a smaller number and work with that number instead. Okay, so here's the last example. I want you to try it on your own, kind of based on the process that we just went through here. Okay, so this is 5 divided by the 5th root of 8. Okay, see if you can rationalize this denominator, please. Again, it's possible that you multiply by the 5th root of 8 to the 4th over itself and reduce that down, but again, the reducing would be extremely difficult. So if you can reduce it to a smaller base to start with, that's going to make it easier. Okay, so when you do that, if you go through step 1 to simplify our radical by reducing the base, we went from a base of 8. Well, 8 is a perfect power, right? It's what? 2 cubed. So we reduced from a base of 8 to a base of 2, and now we can manipulate this with mental calculations a lot more easily. When we build up our radical to higher terms, we're going to use the 5th root, the same index, the same base, which is now that reduced number 2. And as we work through to build this up, we need the total power of 2's to be equal to the index. So our index is 5, the 5th root. We had how many 2's to start with? 3. So how many more do we need to build up to the total index 5? 2. So this becomes a 2, and now we multiply across the top. 5 times the 5th root of 2 squared, which is 4, all over in our denominator. Again, the 5th root of 2 to the 5th fits this pattern where our index and power cancel completely, leaving just that base of 2. Okay. So you guys can see it's very systematic and it's very methodical. It's not a difficult thing if you understand that process. Again, if you don't understand the process, make sure you ask questions, because this should be something that you can do pretty quickly and easily. One of the keys, though, be able to recognize when you're dealing with perfect powers.